Well, good afternoon. Hoş geldiniz, everybody. Today we are having our first panel on the North Anatolian Fault special case from past to future. We will have three talks in a row combined, and afterwards we will have time for questions and answers, if you like. So I ask you for your patience to wait until the end of all three talks. And our first speaker, Professor Yoshioka Kaneda from Kagawa University, Japan. Ohayo gozaimasu. Yeah. So the title of Advanced Researches and Preparedness for the Next Destructive Earthquake Along the North Anatolian Fault. And the stage is for you, sir.
Thank you, Chairman. Yes, my name is Yoshiki Kaneda. Good afternoon, everyone. I would like to talk about advanced researches and preparedness for the next destructive earthquake along the North Anatolian Fault, based on the research in the Maldives, Satrep's Turkey, and the Nankai Trough project. Okay. Today's talk, at first, I would like to explain to the Satrep's Turkey project. It is a 5 years project. From the 2030 to 2070. Next is the Nankai Trough researches and the Kumamoto earthquake here. And, finally, the disaster mitigation science. Okay, at first, this is the seismicity around the Marmara. Okay? You can see many times. The many earthquakes occurred along the North Anatolian Fault in the Marmara Sea. You can see the seismicity, a very high seismicity along the North Anatolian Fault. As you know, this is a historical earthquake along the North Anatolian Fault. The very destructive earthquake occurred. Basically, from the east to west. It's a very, very severe problem. Already 20 years ago, the Izmit earthquake occurred. And next earthquake, nobody knows. And nobody knows when, where. But in the Marmara Sea is a very high risk there. So this is Istanbul and Tokyo has the same risk of the earthquake and the tsunamis. It's just a severe problem for the both countries. And this is Izmit earthquake at the magnitude 7.6. The corruption and liquefaction and a very, very severe problem. It's similar to in Japan. The earthquake occurred. The severe corruption and severe liquefaction. Yes, last year in the Hokkaido, the earthquake occurred. It's a very severe liquefaction occurred. Yes, this is a simulation of the liquefaction here. Oh. No? Okay, no. Probably it's not.
Is it?
A little bit heavy. Okay, yes, okay. This is a liquefaction simulation. Just a moment. Little bit, my file is a little bit heavy. Just a moment. Okay, I passed here. No problem. Next slide. The liquefaction is a very severe problem. Not only in Japan, in Indonesia. Last year, you remember the Sulawesi Islands earthquake occurred. It's a very severe problem by earthquake, by tsunami, and by liquefaction. And finally, the severe problem occurred. Yes. Next. Okay. It's possible? Okay. This is a simulation of the liquefaction. This is a bank, yes. Here? Yes. This is if you image the river, the tsunami is run up, the liquefaction by liquefaction, the bank is subsiding. It's a severe problem, yes. This is just a simulation. I just from now may explain the SATREF project. This project is four groups is included. The first is observational researches. Second is science simulation researches. Third is civil engineering research. And fourth is social science researches. This is the goal of the project, to develop the disaster mitigation policy and strategy based on the multidisciplinary research activities to provide the decision makers with a newly found knowledge for the implementation to the current regulation. The third is to organize disaster education program in order to increase disaster awareness in Turkey. Finally, to contribute to the evaluation of the active fault study in Japan. So this is This is a first group. This is observational research activities using the ocean bottom seismometer (OBS) and ocean bottom electromagnetics (OBEM) and extensometer deployment. This is just the three kinds of the observation around in the Marmara Sea along the North Anatolian Fault. This is a fault model with a partial locked design. This is a seismicity, more detailed seismicity around here. This is a depth. This is a 20 kilometer depth, 30 kilometer depth. Seismicity is a limited lower crust around here. It's over 20 kilometer. It's very deep. And this is one of the results of the observational studies. This is earthquake engineering research activities using the micro tremor measures for the subsoil investigation. Finally, based on this result, we can develop a simulation for the next generation hazard map analysis. This is a risk communication research activity to regional disaster mitigation and disaster education seminar. This is the example in the Yarovar. This is I would like to show the OBS observation to Turkey. This is OBS from Jamstek, Japan. This is we deployed along the North Anatolian Fault. This is okay. This is again. I explained the fault models with a partial locked region. This is. Second is OBEM observation of the resistivity researches. Third is a cluster displacement measures using the extensometer. It's very, very important as an observation. We deployed the 5 stations along to the North Anatolian Fault. Probably around here is a longer North Anatolian Fault here. So more detail. We measured distance each station here. It is a final result. It's a velocity. Yes, it's very, very important. Finally, the average is 8 millimeter per year. It's moving. The creep is including creep. This is a very important information. So based on these observational results, we developed the model setting cycle simulation. Nobody knows when the earthquake occurred, but based on this result, we can estimate the pattern of the next earthquake. This is along the North Anatolian Fault. This is an earthquake occurred. The red color corresponds to here, and blue is asperity here. This is one of the preliminary simulation results. Of course, from now to the future, we continue to these simulation results and these observation researches. It's to improve these simulation. This is very important. On the next slide, I would like to the tsunami simulation. This is a partial plot calculated by the CADMAS 3-dimensional tsunami simulation model. This is one of the examples of the tsunami simulation here. And tsunami simulation is already applied to 3 places. Next slide. This is a result of our status research project. This is a vulnerability of the location, including the different classes with their weight. How to the difficulty to evacuate from the tsunami. It depends on the tsunami height and the topography from the seaside to the safety place. This is a very important the simulation and the analysis. Next slide. As you know, North Anatolian Fault is basically the strike slip the mechanism. Strike slip is not generate large tsunamis, but actually sometimes generate large tsunamis. For instance, the last year, the Sulawesi Island in Indonesia, a very large tsunamis generated. Of course, it depends on the bathymetry map, bathymetry and landslide and liquefaction. I would like to show you this slide. My colleague, Matthew, Professor Yaruchana-san. Yes, this is a landslide around in the Marmara Sea. So, based on this landslide, this is an example of the tsunami simulation. Normally, large earthquake occurred. Strike slip mechanism. But many people, oh, no, not so many tsunamis will come. But actually, with landslide, a tsunami will come. It's a very, very severe problem. It's just a compound disaster. It's an example of the Indonesian Sulawesi Island earthquake and the tsunami damage last year. It's amplified bathymetric features and offshore landslide and liquefaction. Finally, it's a very severe, many people died. This is a hydropressure tsunami simulation. This is a three-dimensional tsunami simulation and hydropressure. This is one of the simulation. If occurred next Marmara earthquake, so some tsunami will come with landslide and without landslide, quite different. But nobody knows. Next earthquake, the landslide with landslide and no without landslide. So we have to prepare with landslide tsunami effect is very, very important. Next slide is a tremor research result, ground motion distribution. We already construct the surface three-dimensional models. It's focusing the shallow part. This shallow part, the shallow subsoil structure is very, very important for the civil engineering. Next slide. This is a seismic response. Oh, sorry. This is Zenchenbrew. This is some slide from the satellite project. This is a response. This is based on the soil structure and advanced simulation researches. This is a hazard map. Black is a very severe problem, and blue and yellow not so severe. This is one of the examples of the Zenchenbrew seismic response. It's just a simulation. We have to extend along the Marmara Sea, the city areas. It's very, very important for the preparedness. This is just the example. Next slide. I would like to the damage to the oil storage tank induced by the earthquake tsunamis. In the morning, there's some video already the fire at the oil tank. It's a severe problem. How to reduce this fire? This is a suppression of the earthquake damage to the stock oil tank using this system, a friction pendulum system. With system and without system. You can see the blue is without system. The red is with system. It's very stable. This is a simulation of the sloshing here. If the large sloshing is a oil tank fire, easy to do. Yes, This is one of the suppression of the earthquake damage to stock oil tank. Yes, this slide is the risk communication and the disaster mitigation education. We already held in the this communication seminar in each cities. Yes, this is very important to communicate local municipality people and medium people. This is very, very important. So next slide, I would like to show you the Nankai Trough research result. This is a plate coupling here. This is Japan. This is a Nankai Trough around here. This is a result of the GPS analysis between data is 1996 to 2000 only. However, after 2000, earthquake occurred in the off Tokachi, magnitude 8 class earthquake here. And as you know, 2011, Tohoku earthquake occurred. And next, we can see next Nankai Trough, or this is the north part of the Japan, is Hokkaido. And next is a metropolitan earthquake in the Tokyo area. It's a severe problem. So this plate coupling analysis is very, very important to estimate next most dangerous area. This is a coupling with the Nankai seismogenic zone. Usually using the land station of the GPS, GNSS analysis. It's a little bit broad, but using the offshore data, we carried out the offshore GPS survey. Yes, it's very important using the station and the vessel. So this is a more precise, more detailed, more high resolution here. Based on this Nankai Trough and recurrent cycle simulation, I would like to show you here. This is a Nankai Trough. The blue is a coupling area. The yellow is an earthquake occurred. This cycle, earthquake occurred. Then the next cycle, more large earthquake occurred along the Nankai Trough seismogenic zone. Here, this is using the supercomputer simulation. I would like to show you that this is the DoNet 1, DoNet 2, offshore the network system to monitor the Nankai Trough cluster activity. This is very, very important here. This is ENNET. So, next slide, I'd like to show you the new research. It's using the fiber optic cable along the image of the seismological and structure feature. This is a Nature Communication already published. Usually in the ocean floor network system, including the seismometers, the pressure gauges, but without sensors, we can use only the fiber optic cable along the image of the seismological and the structure features. Please compare the another seismometers. This green is only a fiber optic cable. It's very, very important information. So the future, if possible, these cable will be deployed in the Marmara Sea. We can monitor the cluster activity. Yes, this is the pressure shock damage and the Kumamoto earthquake 2060. Yes, this is just pressure shock damage, and main shock will come 2 days later. Yes, this is the same house. Yes, it's a severe problem. And after evacuation, in this Kumamoto earthquake, after evacuation, many people died because of the stress and wrong environment in the shelters and cars. Yes, it's a severe problem in Japan. How to improve this evacuation environment? It's a very, very important issue in Japan. So this is the magnitude of an earthquake. Pressure shock is main shock. Many earthquakes occurred between the pressure shock and main shock. So B value, it's a seismological technical term. The B value is a change before and after Kumamoto earthquake. Just before B value is 0.873, and between plate shock and main shock, B value is a little bit small, 0.803. And after main shock, B value is 1.03. It's increasing. It means its energy is released. Yes, it's very, very important to focus. This earthquake, yesterday's Marmara earthquake occurred. Earthquake occurred in the Marmara Sea. This earthquake is a pre-shock or not? We have to check the analysis of the aftershock and the B value. It's very, very important in the near future. So this is I would like to talk about the Tottori earthquake around here. This is Osaka, this is Kobe, this is my university here, around here. I would like to show you some seismic activity. Between 1970 or the 2001, little bit earthquake occurred around here. Please focus on around here. Yes, seismicity is a little bit increasing here. Earthquake will come. Yes, this is our seismicity in the between the almost 30 years. How to estimate, analyze the seismicity change? The physical model and the data science, or the both? This is it's very important issue in Japan. I would like to show you the future research in the Marmara earthquake. At first, observational research such as seismicity, cluster deformation along the North San Antonio fault is very, very important, and prediction research and scenario about Marmara earthquake along the North San Antonio fault. The third is the seismicity and seismic and tsunami hazard researches based on the advanced research and the technology. Promoting countermeasures for the earthquake and tsunamis, and promoting the disaster mitigation education and the risk communication. Finally, the human resource cultivation is very, very important and significant by the disaster science towards the resilient society. At first, please save yourself. This is a personal continuity program, the family continuity program, and community continuity program, and more large, large view, the national disaster continuity program. Yes. So finally, the disaster prevention expert is in Japan is very, very popular. Self-help, the mutual assistance, and cooperation is very, very important. At the huge disaster occurred, self-help is important, indispensable, and mutual assistance is important and indispensable. So this is a disaster mitigation science. Science and medical science and engineering, it's basically the science, but not only these sciences, but also the social science, sociology, the economics, informatics, and some part is philosophy, psychology, art, law. It's very, very important. Totally, as a multidisciplinary science, we had to prepare for the next the huge disasters. It's very, very important here. Finally, I would like to collaborate the Turkey and Japan for the resilient society. It's just my talk. Thank you very much for your attention.
Thank you very much. We'll have questions afterwards. Okay, this brings us to the next talk. In fact, I'm honored to welcome once again Professor Tim Wright, who was doing PhD in Cambridge and Oxford when the 17th of August 1999 earthquake occurred over 20 years. He has a chapter in his thesis on the Izmit earthquakes. So it's a nice opportunity to welcome Tim Wright again. Today he will talk about the satellite radar interferometry and the North Anatolian Fault. What have we learned in the 20 years since the great Kocaeli earthquake? Yes, stage is yours, Tim. I hope your presentation will work properly, and here you are.
Okay, thank you, and thank you for the invitation to speak today. It's always a great pleasure to be visiting Turkey and seeing old friends and colleagues. So I want to talk about what we've learnt from with 20 years really of working on the North Anatolian Fault using this technique called satellite radar interferometry, but really talking about deformation a bit more broadly as well. This work, of course, as always, is a collaborative effort from a range of particularly PhD students and postdocs and other collaborators, some of whom are listed there, and I'll try and mention their work as time goes through. So, as Tunjai mentioned, during my PhD, the terrible earthquakes happened in 1999, and I was at that point I just learned how to make interferograms, and so this was the data set we obtained for the Kocaeli earthquake. This is what we could do then, and what we can do now is produce countrywide deformation maps. And I want to talk a bit about that journey during this talk. But I want to focus really on the science of the earthquake deformation cycle. So what do we see when we look at different times in terms of how the ground deforms around tectonic faults? And we've learnt a huge amount from the North Anatolian Fault from really looking at it very carefully for 20 years. So here's a simple cartoon map. This is a map view of a piece of the ground with a fault running through it, a strike-slip fault like the North Anatolian Fault. If you wait a long time, then what's happening here is you're gradually straining the crust. You're putting elastic energy into the crust in this interseismic phase. In Turkey, you might get as much as 5 meters in, say, 200 years between earthquakes. And then this line here, which was straight at the start, that was laid down immediately after the previous earthquake, that becomes curved. If we now put another line down immediately before the earthquake, and how an earthquake happens very, very quickly, maybe 20 seconds to a minute of shaking. This line that was originally straight now has this offset in it, and the line that was straight before the earthquake has this characteristic curvature to it. And that deformation phase is what we call the coseismic phase, the deformation that happens during the earthquake. And then in principle that repeats, and that's the cycle. In reality, I just realised I didn't step my I pressed the wrong button on my stopwatch. No, I didn't. I did start it. Okay, here's a real measurement. This is a GPS measurement at a site called Tubi, just the other side of the Gulf. And you can see both that coseismic phase, that step of around 60 to 70 centimetres, and that was the movement that happened during the earthquake of that one site. And you can also see the steady state motion in this particular location. But actually, if you focus in on that area, that time period immediately after the earthquake, and you remove the steady state background, you can also see this curved deformation, which is the kind of post-seismic phase. And that's really important for understanding the properties and the physics of what's happening in fault zones. So I'm going to break this talk into 4 parts, focusing on those 3 phases of the cycle, and then trying to bring it all together. And at the end, I'll speculate a bit about the future of radar interferometry. So for those of you who are less familiar with the technique, this is my 2-slide explanation of how INSAR works. This is a diagram that's not to scale. That satellite is at 600 kilometers above the Earth's surface, and these waves are 6 centimeters long. The satellite is orbiting, it's sending a beam down, measuring the reflections. If the ground doesn't move, then you don't get any change in the length of that path. If there's an earthquake and the ground moves, you basically can measure that small change in the distance between the ground and the satellite. And we can measure that very, very precisely. And that's essentially all we're doing. We're looking at changes in the distance between the satellite and the ground surface. So if we go on to now co-seismic deformation, I can show you what those interferograms look like. I should just stress here that the prediction for this simple model, this elastic model, is that we've got very large displacements near the fault in different directions. So to the south of the fault, we should have points moving to the west. To the north, they should be moving to the east. And the rate of those motions should decay as we move away from the fault. And indeed, that's what we see. These are real GPS measurements made after the, before and after the earthquake. And you can see just to the south of the fault, points moved about 2 meters to the west. Just to the north of the rupture, they moved about 2 meters to the east. And the magnitude of those vectors decays as you move away from the fault. Now, when we look at the interferogram, which I already showed you earlier, we see exactly the same information, but we've got data all over for many, many thousands of points on the ground. They're a little bit harder to interpret. The simplest way to think about these is think of them as contour maps of the ground movement. So these are the contour lines, and each of the contour lines is worth about 3 centimeters of ground movement. It's half the radar wavelength. Where the contours are very close together, you've got the ground is really straining a lot, and when they're far apart, there's not much strain on the ground. What you can see here is you've got a fairly symmetrical pattern. In this case, you've got these tight interference fringes both north and south of the fault, and that's exactly consistent with this idea of the fault slipping here below the surface as well as at the surface. The data for the November earthquake was somewhat similar. The slight difference here is that there's more deformation to the north of the fault than to the south, and that's telling you that the fault has to dip, in that case, dipping to the north. You can take those data and build elastic models to try and work out how much slip happened on the fault at depth in those earthquakes. And this is a very commonly done now for all big earthquakes. Here's at the top there is my model, my very, very simple model from my PhD, showing these 6 segments with different amounts of slip. The highest slip pretty much where we are at this meeting. There's a couple of other models here with distributions of slip, all showing very similar features. One thing to emphasize is one of the controversies at the time was how far west did the earthquake go? And in particular, there was no surface rupture on the Herceg Delta, on the Herceg Peninsula there. And so the geological view was the earthquake had stopped there. The deformation data in everybody's models really requires the slip to continue to the west of that delta, which I notice there's a beautiful bridge on now, which wasn't there last time I came, I don't think. The other thing you can see in these slip patterns is that it's quite spatially heterogeneous. You don't get the same amount of slip in different places. Slip is going down to maybe as much as 20 kilometers below the surface. And in particular, there's a little bit of a lower slip, a hint that the slip at the surface is less than the slip at depth. And that's been known as the shallow slip deficit. And that's an issue if you're using surface measurements of geological measurements of slip rate to try and say something about hazard, you might need to factor in the fact that the slip at depth could be a bit larger than you see at the surface. Similar maps for the Düsseldorf earthquake, again just stressing that the models here have a dip of about 50 degrees to the north there, and there's a combination of mostly strike-slip motion, but also some dip-slip motion as well. So the key findings from these co-seismic studies of those 99 earthquakes, first of all, just very simply, the Earth behaves like an elastic solid during earthquakes. We can model it very nicely like that. The slip, though, has to be spatially variable, and actually in this case the fault dip is also varying along strike. The fault extended further west than the surface rupture, and there's this evidence of a shallow slip deficit. So let's have a look at what happened after the earthquake, the post-seismic motion. Again, the GPS data that were measured here have been really critical, particularly observations by Sami Ergentav's group. You can see in this map here the red vectors are the rates of post-seismic velocities measured 6 months after the earthquakes in February 2000. The blue vectors, which are much, much smaller, are the background rates of deformation. And you can see if you look at a profile from A to B, if you look at the bottom there before the earthquakes, you've got plus or minus 10 millimeters per year of motion, so about 20 millimeters total. And if you look in the north, you've got immediately, at the top figure here after the earthquakes, you've got plus or minus 60 to 90 millimeters of motion. So this really much faster rates of accelerated motion happening after the earthquake. The peak of that motion is away from the fault, 10 to 20 kilometers away from the fault on each side, which is telling you that some process is happening at depth. It has to be somewhere between 10 and 20 kilometers below the surface to reproduce that surface feature. However, as well as that broader scale signal, we also saw from INSAR some very localized deformation signatures. So in particular, there was shallow creep identified. This is on the top left there is work by Ziadin Chakir, and he showed, was the first to identify shallow creep happening along the surface rupture. And this has been confirmed by a couple of other studies. In this one by Iqbal Hussain and collaborators, they were able to look at the time history of the creep and show that it matched with a rate and state friction model. So we were able to learn something about the frictional properties of the fault. More recently, Aslan and colleagues have shown that the creep is still continuing today. So you've got these very beautiful, sharp changes in colour here, right up to the fault. So I guess we're somewhere here, aren't we? And you really see this very sharp change in deformation rate. And that's potentially a hazard that people need to worry about if you're building infrastructure across these fault branches. If we just take a step back and look at that broader rate of deformation, and we can try and relate it to other earthquakes. So one of my PhD students, Tom Ingleby, made a compilation of post-seismic deformation from all the earthquakes that he could find, and he plotted it up on this diagram, somewhat complicated. This is a log-log plot showing the velocity here, what the rate of post-seismic deformation is on this axis against the time of the observation. And because it's a log, we're going from timescales of 1 day, where we're getting rates of 1,000 millimeters per year, to up to 10 or 100 years even after an earthquake. And we're collapsing all that data onto this simple plot. And what you see is you get this rapid decay of motion, and they more or less follow, all earthquakes more or less follow a straight line on this plot, showing that the velocities decay as a function of 1 over the time since the earthquake. That's the data from the Izmit earthquake sequence. So you can see here again, it's showing this beautiful straight line going from a week or so after the earthquake up to a decade or more. Because of that straight line, that actually provides quite a powerful constraint on the mechanisms for post-seismic deformation. One common model that people use is to try and model the subsurface as a viscous fluid. So we shock it with the earthquake and we see the viscous response. Now, if you use a uniform viscosity, these are the predictions for different viscosities, so different strengths of the substrate. And what you can see is there's no single model that matches the data. These give you an exponential prediction. What you need is a range of different viscosities. If you want to match the early post-seismic, you need something very, very weak. If you want the late post-seismic, you need something quite strong. People sometimes combine multiple viscosities in a so-called Berger's model. That doesn't work very well either. What does work very well is a rate and state frictional after-slip model, and that predicts a 1 over T decay. And that's actually the same as Amori's law for aftershock decay for any seismologists in the audience. You can also match the data with power law creep. So this is where the material gets weaker as it gets sheared. You need quite a high power law exponent for that to work. So the key findings, I think, for this post-seismic phase, that there was deformation at depths of 10 to 20 kilometers. We had shallow afterslip occurred and is still occurring today. That we have this Amori's law decay for post-seismic deformation. And to explain everything, we need a combination probably of afterslip and some kind of relaxation probably of a high-end power law material in a shear zone. So let's look at interseismic deformation. And this is something I worked on again during my PhD. And this is one of the main results. This took about half of the PhD to produce this one figure, and which you could probably do in about 5 minutes now. But we didn't know what we were doing then. So this is a map of interseismic deformation from combining lots of interferograms together across the fault. And that change in color is this, if you look at a profile, it's representing that change in velocity across the fault. And that's basically the shearing of the material, the build-up of elastic strain around the fault. That's building up that elastic energy that's eventually going to snap in the earthquake. So we want to measure this because this is what gives you the earthquakes, that build-up of elastic energy between earthquakes. As well as that broad-scale deformation, so this is happening on a length scale of 100 kilometers, 50 to 100 kilometers. You've also got shallow, localized deformation, again, interseismic fault creep at the surface, most famously at Izmit Pasha. This is a wall that was built in 1957 that's gradually becoming more increasingly offset. It's a very nice paper by Roger Billim describing that increasing offset of this wall, which hopefully will never be knocked down because it's a fantastic record of that process. INSAR has been incredibly useful for mapping the spatial extent of that creep. So there's a number of studies here showing that fault creep really is that sharp line again. It's taking place over a distance of something like 120 kilometers of the fault. And there's really interesting studies now relating that to the local geology that are coming out. One of the perhaps most exciting things that's come out in the recent literature is a study by Rousset et al. And they looked at some very high resolution INSAR data for a section of the fault. And these are different profiles across the fault at different times. And you can see initially there's no step, and then you get this sudden step appearing here. And if you look then at the time history of motion across the fault, what you see is there's nothing, and then over a period of a month or so, you get this sudden change in the deformation here. So although we see this, what looks like steady creep, actually that creep is happening as a series of slow earthquakes in this location. It's not steady in time. But I really want to focus on the broader scale deformation again and what that tells us about the crust and the build-up of strain between earthquakes. So Akbar Hussain, as part of his PhD, used MVSAT data acquired in the 2000s to map motion across the whole North Anatolian fault, produced these beautiful data sets. I'm not going to go into the details there, but what you can do with those is combine them to produce east-west velocities and vertical velocities. And again, those east-west velocities show this change in color across the fault, which is that build-up of elastic strain. What you can then do is take profiles through that data in different locations, and you can project the data onto these profiles along with any GPS, GNSS data, and you can then fit a model through each of those where you solve for the slip rate and the depth below which it's locked, and a few other parameters as well. In the locations where there's some creep, you see a step, as well as this long-term locking, and you can solve for that step as well and remove it. When you look along the whole fault, what you see is actually a pretty simple pattern. Pretty much everywhere you look, you see these sigmoidal arctangent shapes that are pretty similar, except for those few places where there's a bit of creep at the surface. So you can then take those data and you can look at how properties vary as you move along the fault. First of all, if we look at the slip rate, what you see is in the east, the slip rate from geodesy is about 22 millimeters per year. This increases to about 26 millimeters per year in the west. So there's a gradual increase of slip as you move along the fault. And that's telling you that you've got to have some internal deformation within Anatolia. You can't, it's not simply a Euler pole plate tectonic kind of rotation. The depth below, the depth of locking, so the depth above which the fault is stuck and accumulating strain, is roughly constant, so it's about 16 kilometers on average. And you can use those numbers to calculate the strain rate. And what you see is the strain rate everywhere once you've stripped out that shallow creep effect, is pretty constant as well, and it doesn't seem to relate to the time since the last earthquake. Once you've got this, what you can do is then replot the data. So for every measurement, you can look at when the last earthquake happened in that location, and then you can plot each of these dots is then the strain rate as a function of time since the previous earthquake. And there are three data sets on here. The first is those numbers from Iqbal Hussein's PhD, derived from INSAR and GPS. This is a really critical number. So before the 1999 earthquakes, there were GPS measurements made by McCluskey and colleagues. And so that's that one red dot there. And then these green dots come from post-seismic measurements after the 1999 earthquakes from Ergintav. The essential result here is that if you ignore that decade following the major earthquake, the strain rate is constant. And that's quite a surprise, actually. So the key findings here then, strain rate is independent of the time since the earthquake, except for the decade since a major earthquake. The present day strain, therefore, is a reliable indicator of future hazard. If the strain rate doesn't vary, if you can measure the strain now, the strain is going to be the same whenever you measure it, and that's then useful for saying something about the likelihood of future earthquakes. And these areas of shallow creep exist, and they may be partly, at least, areas of long-lived afterslip. So we try and bring all these observations together in a model for the whole earthquake cycle. So we can use this is a very old model, but a very simple model that kind of helps us get our head around what's going on. Essentially, this model has repeated earthquakes in a layer in this elastic lid above a viscoelastic substrate. So that material, a viscoelastic material, is elastic on short time scales, but flows like honey on a long time scale. So we have repeating earthquakes there, and essentially there's one parameter that controls everything, and it's related to the viscosity of the substrate. Again, like we saw for post-seismic data, we can then try and model this. And here's the data from Iqbal's work, again, those red, blue, and green dots. If you look at different models here, this is a very low viscosity model. You need that to match this very early time period. But it can't match the late. It gives too low a strain late in the cycle. As you increase the viscosity, what happens is you flatten out the curves. So once you get up to 10 to the 20 or 10 to the 21 Pascal seconds, you end up with basically the same strain rate at the beginning of the earthquake cycle as the end of the earthquake cycle. You can't match the post-seismic deformation like that. So we have a problem here. This model basically doesn't work. So how do we fix it? Well, what you can do, you need a separate material, separate area that's relaxing in the post-seismic material, and that has to follow this Amori's law with the 1/T decay. So that could be afterslip, it could be a low viscosity power law material in a zone around the base of the fault. Both of those types of model will work, and if you put those in, you can match the whole earthquake cycle with a single model. So essentially, the constraints here, the key numbers here, though, really are that the strain rate, the fact that there's a constant strain rate after that post-seismic period requires a relatively strong substrate. So you need a viscosity greater than something like 10 to the 20 Pascal seconds. The relaxation time has to be long compared to the time between earthquakes. And we can explain the whole earthquake cycle if we have something weak and relaxing quickly embedded within that stronger material. Okay, so I'm going to end by just talking a little bit about the technology and way that technology is going in the future. So again, this is my PhD, so this is kind of, well, it was about half a PhD's work to produce this one figure. It covered about 20,000 square kilometers. But a pretty tiny area. So by 2009, Richard Walters had covered about 250,000 square kilometers. In Iqbal Hussein's work, he covered about 750,000 kilometers. Now, and again, a lot of intensive work now. What we're doing is now trying to automate this process using new data from a satellite called Sentinel-1, and we can process that semi-automatically. So this is some early results from that. So what we do is we break up Turkey into frames. We calculate the velocity by using all the data from Sentinel-1. It's about 4 years of data in this current plot. You can then do it for the whole of the country in the same way. As the satellite's traveling north on these ascending passes and as it's going south on the descending passes, you can combine all of these then to give you these two components of the velocity field. At the top, the east-west velocity, showing again very nicely that change in color across the North Anatolian and East Anatolian faults here, but also the vertical rates. And you can see there's lots of interesting features in the vertical that are non-tectonic. They're largely to do with water extraction, mining, and other features. But there's lots of interesting and valuable information in here as well. You can turn those numbers into strain rates, and this is again a preliminary result combining the INSO and the GPS to map the rate of tectonic strain. So that should be related to the amount of seismicity there is in a given area. So if we then compare that to the current seismic hazard map, you can see there's a very nice correspondence actually between where the ground is straining and where the seismic hazard is predicted to be. It's not quite as simple as a one-to-one transformation between these two things, but I think this is somewhere we'd like to go in the future, is incorporating these measurements of strain into future versions of the seismic hazard map. And we're trying to do this not just in Turkey, but within the COMET group, we're trying to cover a much wider region, to cover the whole Alpine Himalayan belt. If you go on our website, we've got something like 200,000 interferograms you can download. I just picked one here from Turkey. This is one showing the earthquake, the 5.9 earthquake that happened in August in southern Turkey. And all that data is there, available, download for free for you to use and analyze in your own time. So I want to leave it there with some take-home messages. So I think the North Anatolian Fault has provided the best geodetic data set for understanding the earthquake deformation cycle anywhere in the world. It's really an incredible data set, and we've learned so much about the processes by looking at it. I want to stress that models need to explain all of those phases of the earthquake deformation cycle. There's lots of models been generated in California where there hasn't been a big earthquake on the San Andreas. They won't work, I don't think, when there is an earthquake. And then these new advances in geodesy are providing really sharp images of strain, which I think will be important for seismic hazard estimates. But probably we can't use them by themselves. I think we need to combine those geodetic data with other constraints from seismology, from geology, etc. And I think we'll hear some more about that in the next talk as well. So I'll leave it there. Thank you. Thank you very much. Okay.
So that brings us to the final talk on the panel. And again, I'm glad to invite Professor Gregory Hausman once again to our Anatolian lands, and he will now give us the reason why the earthquakes occur in the North Anatolian Fault, and he has all answers, and we'll see in a minute. I think it's...
Maybe I'll let you open this one.
Is this...
No, it's the middle one.
The middle one, that's the one. Okay.
Yeah. We want it open on Adobe, yeah, thank you. Thank you. Thank you, Tunjay, for the introduction, and thank you to the organising committee for inviting me out to make this presentation. I'm very pleased to be a part of this commemoration of what was a disaster for this area, and I was very interested to hear all the official presentations this morning about, just to give a kind of idea about the impact that this 1999 events have had on this region. As the other speakers have said, the kind of work that we've done has been the outcome of much collaborative work, and I'm here really to tell you mainly about a project that we did in 2012-2013 together with partners from Kandili and from the University of Sakarya. And we had a lot of cooperation from local people involved in putting out a seismic network. So I guess maybe I will start from a fairly basic level in this, but I think it's interesting for some people here who maybe are not seismological specialists to just have another look at the map of seismicity in Turkey. And of course, these are recent earthquakes, only since 1997. The North Anatolian Fault is evident, the Hellenic Trench is evident, the East Anatolian Fault, lots of activity in Western Turkey. But we're here mainly to talk about the North Anatolian, but it's important to be aware of the whole picture in this. And the reason why there are earthquakes on the North Anatolian Fault, at one level, this is a horrendously complicated problem and there isn't a simple answer. But at another level, you can look at this map of GPS vectors. I think Tim showed something like it. And in this map, the effect of earthquakes has been taken out. And what we are looking at here are the measurements of points on the ground taken over a longish periods, over the period of years. The whole of Anatolia is moving westward and to the southwest. I think many of you are probably aware of this. As Tim mentioned, it's not simply a rotation because you can see the vectors here increasing in length as you head towards the Hellenic Trench, up to about 40 millimetres a year. And that increase really represents the effect that the Anatolian region is being stretched. And so we have activity which is affecting the whole of the region in a very dramatic way. And furthermore, when you look at this map, you don't really see the faults. What you see is something that looks like the flow field of something like a glacier. That is, it's controlled by some kind of viscous flow. And if we ask how that can be, we're led fairly rapidly into the idea that it's controlled by some kind of viscous layer, that the lithosphere is deforming by a kind of creep. Now, yes, the earthquakes happen, and yes, there is elastic strain on the upper layers, as we have just heard from Tim's excellent talk. But the overall motion appears to be controlled by viscous flow. And that is what we think it is. It's most of the lithosphere, but between depths of about 20 and about 100 kilometres. The whole of the lithosphere is creeping gradually. And so we can make actually dynamical models of this viscous flow. And on this map, what we've got here are the black vectors being data and the red vectors being the model from a rather simple viscous flow. So this is just to illustrate that we can actually make a very acceptable fit to how this deformation is occurring on the large scale, driven by the fact that we have very high topography, high gravitational potential energy over on this side, and very low gravitational potential energy because we have a subduction zone which is rolling backwards on this side. Now, as Tim showed a similar figure to this, if Turkey overall is behaving with a deformation that is represented by this continuous viscous flow, then what happens at the surface? How do we deal with this? We have some kind of incompatibility, and it's a difficult mechanical problem to represent this exactly or precisely, because both of these materials have elastic strain built up in them, and they have viscous creep occurring. But those two things are occurring in a rather complicated way. They can trade off against each other. Tim showed this figure also, the relative motion. And what I wanted to point out here, and which he showed in his final figure, which is actually a better figure for this point, is the fact that we've got this steep gradient along the North Anatolian. So it's clear that although most of Turkey is behaving like a viscous sheet, the deformation around the North Anatolian is stronger. It's more concentrated. And what does that say? It's saying that the lithosphere beneath this fault region, which may be tens of kilometres wide, is relatively weaker. So that is an important point that we need to get into any models that explain what's going on. The problem is, what does that mean? Why would it be weaker? We've seen this picture of the westward progression of the earthquakes, and I don't think I need to spend any time on this. We've seen the fact that that we had the interferograms and how these have given us very accurate measurements of what's happened in the Izmit region, so I'll pass on to that. I think it's very interesting, the historical record in this paper from Barker et al. In 2002, showing earthquakes in the Marmara region in the 18th century, in the 19th century, relatively less active, and of course the big earthquakes in 1999. So one other thing that is interesting from this map is the density of fault traces in here. In some sense, it's very attractive to think of the North Anatolian Fault as a sharp trace, but in fact what we see in repeated regions is that there are multiple fault strands. They weave in and out of each other. Sometimes one will move in an earthquake, sometimes another one will move in an earthquake. Again, there's an implication here that this fault zone is actually, although it's creeping rather rapidly, that the creep is distributed over something like tens of kilometres at depth. So back around 2010, Tim and I and others at Leeds got together with the idea of having a project that we would attempt to get some images of this deep structure of a major fault zone, and we thought that the North Anatolian Fault was actually probably the best one to use. So we were fortunate to get funding from the UK NERC and with several objectives. One was a seismic experiment that I'm going to tell you about. The other was the geodetic analysis, which you've essentially just heard about, and the geodynamical models, which involved the development of a 3D viscoelastic continuum mechanics program. Part of the motivation for this was just the fact that we don't really know what is underneath one of these major strike slip faults. These are a couple of images that were published by Alain Vaucher, I think around the time of our project, and these are kind of maybe a best guess of the fact that yes, there probably is quite a sharp discontinuity in this uppermost layer, and then what happens down below. I guess the best guess is that it's some kind of distributed shear zone, because when we see the energy that comes from an earthquake, we see that it only comes from these upper layers. And yet we know that there must be some compatible deformation going on underneath. And in fact, the models, the types of earthquake cycle models that Tim has mentioned, tell us that this viscous creep in the ductile layers must be, to some extent, what is actually allowing the elastic stress to build up in those upper layers. So I'm going to tell you now about the seismic project that we did, and we set out with the objective of putting a set of seismic stations across the North Anatolian. So here's the northern branch of the North Anatolian fault near Adapazari. This is Lake Sapanja. This is the Sakarya River. The fault has quite a complex structure here as it goes around the, I think it's called the Almacic region. We have a floodplain in here, which is basically caused by a pull-apart basin, and the Sakarya River goes through the Pamakova Basin here, again through the pull-apart basin, and then there's another major branch of the fault down here. So the objective was to put seismic stations on something like a 70 kilometre by 30 kilometre grid in order to get the best possible seismic images. This was quite an expensive project in a sense, because it required a lot of effort to get all these seismographs out there and installed, and a lot of people were involved in the project to put them in. This is what our stations look like. They're very basic. A seismic sensor in here, a data storage which is on board, some instruments to power the device, and solar panel, of course, to actually provide the logic. We had a lot of support from local people in doing this. This is Professor Turkelly from Koeri. Dr. Oz Ghosh, who was with me in Leeds at the time, is now at ITU. This is one of the stations that we had. While we were putting this in, we were getting advice about how to actually dig a hole from the people who lived there. And one of the great things about this project was just the interaction we had with the many different landowners that we had to go and talk to in order to say, is it okay if we put a seismic station on your property? What will, people were very supportive. They were glad, I think, to know that there were people coming to their area who were interested to study the earthquake, and some of these people had been very badly affected by the earthquakes. So these are just some of the pictures. We had tons of equipment. The main sensors that mainly came over from the UK. Some of the people involved, Sebastian Rost from Leeds was one of the PIs. You might recognise Selda, Altunku Porras, Metin Karaman, Murat Utkucu, and it was, for me, a great privilege to be involved in this project. Selda put together this map of the local seismicity using all the data we got. It's remarkable for me in various ways, one of which is that the local seismicity is not very closely related to the fault traces. In fact, there's a very strong alignment of seismicity which is kind of conjugate to the main traces of the fault there, and which maybe somehow is related to the fact that the Sakarya River flows through this zone. The seismicity, as you might expect, is predominantly shallower than 10 kilometres, and there's very little, I think, if anything, that gets below 20 kilometres. We've tried various approaches to analyse the seismic data in terms of attempting to get some imaging. This is a study that came out this year by one of our PhD students, George Taylor, and he looked at the ambient noise correlation between all of the stations that are shown there, and used that to do a surface wave analysis and to produce maps of the seismic velocity. Because of the frequencies that were available on this technique, because of the size of the array, it's relatively shallow. But at 1 kilometre we can see that there's a reasonably slow anomaly on the north side in what is referred to as the Istanbul zone. Between the two strands of the fault, it's relatively fast at 1 kilometre, and that seems to continue down to the maximum kind of penetration we've got at about 5.5 kilometres. If you're not familiar with these kind of images, you might think, well, this is a very blurry image. It's not a very clear picture, but I think what you have to bear in mind that with seismic waves that travel at about 6 kilometres a second, and if we are measuring the signals that have a frequency of about 1 hertz, that we don't get very good resolution. We can go to higher frequencies, of course, which is how we can get to these kinds of pictures, but still we're very limited in what we can actually do with seismic waves. Another study, the first author is Papalio working with David Cornwall, and here what they have done is to look at distant earthquakes from different parts of the world and how those signals come up through the crust and interact with our seismic array in order to map regions that are relatively slow or relatively fast. And so these are sections through perpendicular to the fault. Those are 2 strands of the fault. We have 3 maps at different longitudes, and what you can see is something that appears relatively fast going through the crust between the 2 strands of the fault, and something that is relatively slow dipping down to the north on the north side of the northern strand, and again relatively slow material on the south side of the southern strand. They produced this 3D block image, which is a little puzzling to look at. I'll try and explain it. It's the same model shown from two perspectives. This is from the southeast side, and there's the slow material dipping down through the crust towards the north. There's the northern strand of the fault there, and the southern part of the fault is relatively slow also. So in between, we've got this kind of block of relatively high velocity material. So it's, again, difficult to make clear conclusions from these rather blurry images, but one thing that we can see is that there appears to be some kind of broadening with depth that might be part of the story. And we can compare this with another type of measurement which was published some years ago by Bullet Tank, and this is showing electrical resistivity. And this, again, is going more or less through perpendicular to the North Anatolian Fault around the longitude of Adapazari, and it's got low resistivities in the lower crust and the upper mantle. So again, something special underneath the fault, but again, fairly blurry image. So the other attempt, the other way of analysing these data, which has maybe been a bit more successful, again, you might think the images are fairly blurry, but this one, what we do is we take those signals that come in from more distant earthquakes on the other side of the globe, or not the other side, but thousands of kilometres away. The earthquake waves have come up through the Earth. When they hit a discontinuity in the velocity, they change from compressional waves to shear waves, and we can analyse how long it takes the shear wave to travel up there, and how big is the converted signal. So this map shows the signals that have come from many earthquakes to many receivers, and which have sampled that big conversion where we change from the crust to mantle in order to produce an image. And this was put together by Metin Karaman and others from the group. And I think this is probably the most interesting image that was produced from this analysis. It shows that we have horizontal structure where the seismic velocity changes. That's at a depth of about 10 kilometres, and it's truncated more or less at the point where the southern strand of the fault is. It's offset a little bit beneath the northern strand of the fault, and then this reflector, which represents the major velocity discontinuity of the crust-mantle transition, fades out more or less in the same region. So we're inclined to think that there is some kind of discontinuity in here. There is something that affects the strength of the converted signal in here, which may be conceivably something like the peridotite of the mantle being converted to serpentinite, or that's one possibility. But one of the important things here is that we seem to see the effect of the fault penetrating down right through the crust, right through the upper 40 kilometres, even though we know it's only seismic in the upper part of the fault. This other section is further east, and again, we see structures that are truncated by the strands of the fault. Okay, Tim showed this this picture of the North Anatolian Fault, and I'm not going to dwell on this, but I'll just comment again on what we get from analysing the post-seismic activity compared to the pre-earthquake activity. And as Tim mentioned, this signal, we go from before the earthquake, where we had about 25 to 30 millimetres per year of contrast across this 50 kilometre wide zone of the fault, as shown by GPS signals, and to an immediate post-seismic signal, which went between 60 and 90 millimetres a year. We tried to model this using the viscoelastic program that we developed in Leeds to see what we could get out of this. The work was done mainly by Tadashi Yamasaki, who was working at Leeds with us. What we did was to set up a model. It's very simple in concept, which is that it's viscous underneath, it's elastic in the upper part. The elastic part is cut by a fault, and we drive the sides at a constant rate, and we let the fault catch up on a cyclical kind of frequency, and then ask what happens. Well, Tim has already mentioned the result that in order to get these high rates in the immediate post-seismic period, as well as the relatively gentle change in velocity before the earthquakes, we need to have some kind of low viscosity structure underneath the fault. It needs to be maybe a factor of 100 less. So there's some very interesting questions to ask about what could be this low viscosity structure. Is it a zone of damage? Is it a zone where fluids have infiltrated? Is it something related to heating? I think these answers need further research. But something needs to be there, or we cannot get these high rates predicted. I guess I've given you a different perspective from what Tim has, and I think it would be interesting to actually look harder at the question about whether you can explain this just by what's going on the fault, or whether this low viscosity zone is sufficient to the purpose. But having argued for the fact that we need a low viscosity zone that is 20 to 40 kilometres wide, right underneath the North Anatolian Fault, and arguing for the fact that it's a low viscosity zone, it certainly got me thinking when I looked again at this image, and I see this zone of blue in the image at about the interesting depth to explain this, and I'm thinking, well, maybe it's present in the seismic too. Seismic velocity is a very different parameter from viscosity, but they are affected in similar ways by temperature or by fluid content. So this is something, again, that needs further study, further thought. I won't comment on this perhaps, except just to say it's another way of looking at a point that Tim made, which is that at present, the creep rates across the North Anatolian Fault will more or less follow this red dotted line, but in the immediate post-seismic period, they decay very rapidly back to this particular point. And I'll conclude just with a few concluding statements. Firstly, that Anatolia is moving westward relative to Eurasia continuously. Okay, so that motion is always going on in the background. It's driven by these large-scale differences in gravitational potential energy. It is not going to stop, so the earthquakes that have been happening in the past will happen again. The rates of deformation are well explained by a model of viscous deformation in the upper mantle, with earthquakes arising from the movement on faults in the upper 20 kilometres or so of the crust. The North Anatolian fault system has developed along a relatively weak alignment, parallel to the main velocity field, and it experiences the greatest strain rates and the largest earthquakes in the region, but there are, in fact, a high risk of seismicity in many other regions of the whole of Anatolia. The seismic imaging of the part of the fault that moved catastrophically in 1999 reveals that the fault has truncated structure right through the 40-kilometre thick crust and probably into the mantle. That truncation of structure is stronger on the northern strand than it is on the southern strand, but it's evident to a slightly lesser degree on the southern strand as well. And the relatively rapid post-seismic creep near the fault in the months following the 1999 earthquakes implies to me a low viscosity layer in the mid-crust below the fault zone. Thank you.
Questions and answers, if any open questions left. And the session is open for discussion, questions, comments, critics. Yes, please. Quick one.
The risk. Ergen Ulutaş, Kocaeli Üniversitesi. I will comment to Professor Kaneda's presentation. He emphasized that the seismic, the risk and the hazard is the same with the Tokyo and Istanbul. As a term, yes, it's the same, but as a result may not be the same. So, for the tsunamis, I will say something about this. For example, in the after the Tohoku earthquake, in the Pacific Ocean, the initial height and the Marmara is the initial height may not be different as we compare the simulations. So, for example, the depth of the Pacific is 7,000 kilometers, but in Marmara Sea, maximum 1,200 meters, or in some of the parts, for example, 500 meters depth. So, I agree with you, with the landslides is important for this area. So, for example, did you calculate something about the Çınarcık Basin, for example? What is your worst case scenario for the Istanbul if there happens an earthquake and the landslide together with the basin? 1 meter, 2 meter, 3 meters?
Mikrofon alabilir miyiz?
Thank you for good questions. At first, the Istanbul and the Tokyo is almost a similar population. It's very, yes, the high risk. And maybe if there occurred the metropolitan earthquake in Tokyo, the estimated the victims is about over 2,000 people die. It's a little bit similar to the Izmir earthquake. Yes, I think so. And your question about the seismic hazard map. Yes, hazard map. In Tokyo, and there is many soft sediment area. It's easy to occur liquefaction. For instance, the 2011 Tokyo earthquake in the Tokyo area, especially the Disneyland, the Tokyo Disneyland area, it's very severe liquefaction occurred. It's similar to around the Marmara Sea. So it's all same hazard map, I think so. And second,
The worst case scenario for tsunami is the maximum.
yes, I know. This tsunami simulation, and it's presented, researched by the Professor Yarchinaru and his colleagues, and we already carried estimate the bathymetry map around the Marmara Sea, and we can estimate the past landslide area. So we can calculate the volume. So finally, the worst scenario is that all area is occurred landslide. It's probably maximum tsunami height over 3 meters, about, yes.
Shall we leave this discussion to the later? Okay, if otherwise it's quick. Yeah.
So, but in Marmara Sea, time is not enough for this. So, maybe a little bit more, but I agree with you for the landslide, and the important is much more from the inundation.
Yes.
Okay, we will leave that.
Thank you.
And there was a question or somebody's... No further comments? Okay, please. Not only for the Canada Sensei, but for the other panel members too. So we are expecting questions and discussions.
Very thanks, President. I have questions, Professor Tim Wright. At the post-seismic INSAR on the North Anatolian Fault, Izmit Gulf and Sapanca Lake, how much kilometers deformation zones between Izmit Gulf and Sapanca Lake of north and south direction? how much kilometers? And post-seismic INSAR and co-seismic INSAR. Do you have different deformation zones with? Thanks.
Microphone, please.
Thank you. Thank you for your question. So the question is about the width of the post-seismic and co-seismic zones. The easy one is the co-seismic. So for co-seismic, you need, the deformation is spread over a very wide region, and you need slip on the fault to go down to around 15 to 20 kilometers below the surface, and that spread deformation over a range of something like 50 to 100 kilometers away from the fault in terms of areas that moved. Now, the GPS is showing that for the post-seismic, it's also over a similar range. There are two mechanisms going on with the post-seismic. One is something going on at depth that might be continued movement on the deep part of the fault, or it might be relaxation of a low viscosity zone, that is happening at a depth of around 10 to 20 kilometers, giving you those peaks in deformation that are 10 to 20 kilometers either side of the fault. So again, a signal that spreads over 50 to 100 kilometers of width. But there's also a very narrow zone of afterslip very close to the fault, and that seems to happen, that's very localized, I think. So that will be, you could probably go up to you probably put your finger on it almost, certainly where people have seen these in other locations, very, very sharp. From the INSAR, all we can tell is that between neighboring pixels, there is a discontinuity. So it looks very, very sharp there. And that's probably only in the upper few kilometers that extends. But at the surface, it's very, very localized. I hope that answers your question.
Okay. Yes, Levent, please. And afterwards, Dursun, but the quick one, okay? Very short. Okay. Microphone. Bir tane mi mikrofonumuz var? Ha.
Thank you for your presentations. My question is for Tim. In your Greg mentioned about a low velocity layer, and in your modeling, do you take into account that mid-crustal low velocity layer as a low viscosity layer and so on and so forth?
Thank you. So, well, first of all, I guess I was also involved in Greg's study where we did explicitly modeled this weak zone in the lower crust. The models I presented in my talk were much simpler. They just had uniform properties in the substrate. And the idea there was to really show that that model didn't work. Sometimes you learn more by learning that a model doesn't work than you do by learning that a model does work. So what you learn from that model is that you need the viscosity. Most of the, and we also learned this from Yamasaki, the Yamasaki paper, is that we need most of the material to be quite strong, so have this relatively high viscosity, and then there needs to be something else that relaxes quickly to give you the post-seismic signal. Now you can do that with a broad low viscosity zone. I think you can also probably do it with slip after slip on the fault. What we didn't do in the Yamasaki study was look at the time history very carefully. We just looked at two points in the whole earthquake cycle rather than try to model the entire cycle. And I think if we were doing it again, we'd use the data from Iqbal Hussein's compilation and try and model the whole earthquake cycle. I think it wouldn't change the spatial pattern very much, but we'd probably need a more complex rheology in that zone. I don't know whether Greg wants to comment on that.
My only comment is that I think that's a good idea to do it and see what the answer is. Yeah.
And the very quick one, Dursun, please.
The question is to all our visitors. In Japan, during the fault fracturing, the fault making a water suction to the gap. And after we saw after earthquake, the plates moving slowly. And then maybe the low viscosity layer with the same principle during the opening, and then maybe the laterally water condensing inside of the long gap, and it can make a low friction effect, maybe the reason of the problem. I'm asking all of you.
Yeah.
Thank you very much for your questions. But in Japan, your question is actually sometimes because small micro earthquake. It's a shallow part, okay? It's not a deep part. So, for instance, the dam after the dam construction, earthquake occurred. Yes, small earthquake occurred. Yes, it's a similar scenario. The water is induced in the rock, and the fracture is generated. But it's just a part of the shallow part, not the deep part. More questions about it?
I'll just add a little to that based on my work with the seismic imaging and the effect on the receiver functions. That is, those seismic waves that come up and hit the MOHO and then get converted to shear waves and arrive at the surface later on. In major fault zones, it seems common to find that conversion is broken. It's disrupted for some reason. It might be distributed over some distance. Now, I don't know exactly what the answer to this is, and we can't sample it because we're talking about things that are at 40 kilometres depth. But it seems to me plausible that having water penetrate down through the fault and reaching that conversion where it can actually interact with the peridotite and change the properties of the materials is one way that we could get rid of that conversion. So I'm quite open to that idea, but I don't see an easy way to demonstrate that it is a valid idea to be clear that water is actually getting down there.
I think I just add one covering a different perspective again. So there are some nice examples in different parts of the world for poroelastic deformation where you can clearly relate motion of fluids in the pore spaces to post-seismic deformation, most notably in Iceland, where you see a very nice correspondence between levels in the water wells and deformation happening after the earthquake. And I think it's again very plausible that there would be some very strong links between the fluids and the processes going on the faults. And I think it's an exciting area for future research.
Yeah, thank you very much for those comments and critics. If it's very short, okay, we are running out of time. Just one last one. In the meantime, I can add one comment to that one because there are some studies on the fault plane trapped waves for the phase changes along the North Anatolian Fault and San Andreas Fault, mainly the Yehuda Benzion's paper, and also some examples like, as you said, in Iceland and Greenland. There are effects for the Dursun question. You should read some of those papers, Dursun. Okay.
I want to ask a short question to Professor Tim Wright. He mentioned in his speech step-like creep in Bolu İsmet Paşa section of the North Anatolian Fault Zone. I wonder if what you call or what you name this step-like creep in that area. A slow earthquake or silent earthquake? Which one is the best explanation?
I think, yes, so the idea of these are not steady in time. I think you can call them slow earthquakes if you like, or silent earthquakes. I think both are fine.
Both,
I
yeah.
think the slow earthquakes perhaps more commonly seen in the literature, and actually seen a lot of these events on subduction zones in particular, and it's only now that we're starting to see them on strike slip zones as well. They can be silent as well because there's no seismic waves coming off these as far as we know. There could be some seismic signals, I guess, but these are very, very slow. They're not producing typical earthquake deformation.
Okay, thank you.
Yes, thanks for that. And I think slow earthquakes definitions fits better than the silent ones because that's the common terminology we use for the megathrust earthquakes in subduction zones. So I received a note from the president of the organization, the lady, Right Honorable lady over there, gave me another opportunity to invite the speakers from the other halls and to present their gift of attendance for this very exciting panel and also the parallel session. So may I invite, in order, Professor Dr. Mahdi Motank to the stage, and also the Professor Dr. Bülent Oruç is here to present his memoir of the symposium. Over there, please. Yeah, maybe just here because they will take some photographs of whatever. No, you hang on. I will call you in order. Okay, just here, please. Okay, stand here. Okay. Oh, maybe over here much better. So because I will ask everybody to stay on the stage. Okay. Afterwards, yeah. Professor Mahdi Motak and Bülent Ortaç from Kocaeli University. Yep. Thanks for attendance. Okay. And I will ask you to stay on the stage. And in the meantime, may I invite Dr. Özdoğan Yılmaz, to the stage, please. Basamak var mı burada? Well, according to the list, I was asked to present this small gift on behalf of the organizing committee to the Dr. Yılmaz. Thanks for your valuable comments. May I kiss you in Turkish way? Congratulations. I've enjoyed your talk. And also, may I invite invited speaker Dr. Murat Nurlu to the stage, and also Professor Dr. Nilgün Sayıl. Is she here to present his gift of attendance? Böyle de gelebilirsin. So there will be some archives of photographs for the memoirs. Nilgün Hanım'a verir misiniz? Okay, don't disappear. Okay, you'll ask you again to the stage. And Professor Tim Wright, please. And the Professor Eşref Yalçınkaya, is he around? Yes, for the gifts. I don't think you need a certificate of attendance. This is a Turkish, I don't know, you may be finding this silly, but this is necessary in Turkey. I don't know, but. And Professor Murat, Greg Hausman, please. And also Dr. Murat Utkucu. Professor Murat Utkucu, or Doctor, I can't read. Okay. And, yeah. Yeah. Thank you very much. And Professor Yoshiyuki Kaneda Sensei Dozo and Professor Dr. Levent Gülen, please. I think finally, I am also going to receive a similar present from Professor Fadime Serçelik, please. Okay. I don't have certificate of attendance. Yes, sabotage. Yeah, but I have Istanbuli here. Anyway, thank you very much. All the best. So, according to the note, can I invite again all the invited speakers to the stage for the group photographs, please? This was asked from the organizer's desk.
With boxes or without?
Please, all participants, please. Yeah.
Nasıl yapalım? Öyle mi?
Please, we are waiting all the participants. Herkesi bekliyoruz lütfen.